questions that you may have concerning the classification of point groups or identification of symmetry elements and operations in any given molecule and be able to establish the point group. I think last couple of lectures we have spent quite a lot of time in terms of identifying the symmetry elements and which form the basis for us to go back to the chart. So when you're taking the exam, you will be allowed to keep the chart next to you. We would not expect you to memorize everything, except that you need to be able to identify the elements and be able to answer the questions. So at this time, I would like to ask the class if they are experiencing any issues with the identification of symmetry operations or elements, and also any trouble dealing with the point group classifications. Because starting next week, the topic will be very different because we have so many topics to cover in inorganic chemistry. So we can be sticking to one topic for a long time. I'm sure you can understand that. Any issues, any questions? Anything that's not clear? That's what we want to clarify today. For some of you, because this is the first experience dealing with the molecular symmetry, there may be some, it may not be always smooth because it takes a lot of practice. I think I told you about this. So let me see if you have any questions. Suppose if I were to ask you, is there, can you all see the board? Suppose if I ask you, does this molecule methane has an improper axis of rotation? Does it or does it not? Because these are all mathematical operations, the answer is binary, yes or no?
Yes.
Where is that, Gurveer?
It'll be S2, right?
No.
Sorry, S4, my bad, S4.
S4, we changed your answer from S2 to S4. So where is that S4 axis? Does it include any of the CH bonds? These are the kind of questions, when you get in the exams. So there will be multiple choice. The molecule CH4 either has S or no S, or does it have an S2?
No, it doesn't include any of the hydrogen.
It does not include any of the hydrogens. Does it include at least the carbon atom?
Yes.
Okay. Is there any other symmetry operation along this S4?
A C2?
Absolutely correct. Is that clear to all of you folks? It has a C2, which is collinear. Watch my language, collinear. That means it's the same line that serves as both S4 and C2. Am I making sense?
Could you explain about the S4 again?
Okay, okay, let's talk about S4 just a second. Gurveer, you can mute yourself. You know where it is, but for others, let's talk about what is S4. And S4 means a C4 followed by a sigma that is perpendicular to the S4 C4 axis. That's very important. That means you have to do two operations before you can get a similar looking molecule, right? So we need to do a C4 followed by a reflection in a plane that is perpendicular to the C4. So let's do this one here. Let's take this molecule C4 as this. Can you all see that? I inscribed the tetrahedra within a cube. When I do that, 2 of the hydrogens occupy the diagonally opposite corners of the top, and 2 of the remaining hydrogens occupy the diagonal spaces in the cube on the other side, in the way it is shown in the picture. Okay. Now, what I'm arguing is it has a S4 that is collinear with the C2. So let's do a C4 on this first. Okay, C4 along an axis that goes through the midpoint here and that and the midpoint of this plane. Can you see that line there? All right, that's your C4 axis. When you do that C4, you get a picture that looks like this. All right, so this molecule comes here, that goes there, and this molecule goes there, and that atom goes there, and the carbon stays there. Clearly, you know that there is no C4 in methane, right? In fact, this operation does not look exactly the way it looks here. Would you all agree with me that this molecule has no C4? All right, so what I'm going to do is now reflect in a plane that is perpendicular to the C4. That's my sigma, because the C4 is along this axis. When I do this reflection of this, what I get is this atom goes down here, and that atom goes down there, and this atom comes up here, and this atom goes up there, and the C remains here. Does it look similar to this? Am I making sense? So there is no sigma directly, there is no C4 either in this molecule. But if you do both, a C4 followed by a sigma, that's exactly what a rotoreflectory axis. A rotoreflectory axis means a reflection followed by rotation, or a rotation followed by reflection, either way. The order of the operations is irrelevant. You can do a sigma first and do a C4, or a C4 first and do a sigma. The order of the operation is not important. However, it's important to have both the operations before you can get a similar looking structure. And that's the reason why we say CH4 has an S4 that is collinear with this C2. How many S4s it has? This is 1. How many C2s this molecule has? One, 2, 3, 5, 10. Well, how many? Remember, we went over this methane molecule in quite a detail some time back. How many C2s did we say this molecule has? How many, folks?
Was it 2 C2s?
In fact, one more. There are 3 C2s.
Yeah.
Okay, it's very important to get that one straight. So for example, if I take the midpoint of this plane and midpoint of that plane and then join that line, right? That's a C2 too. Similarly, if I look at the midpoint of the forward-looking plane and the midpoint of the back plane, join the line, you get another axis that's also a C2. So typically, if you assume carbon to be the origin, and if you draw a Cartesian axis X, Y, and Z with respect to the carbon atom, so those 3 axes, X, Y, and Z, are collinear with the C2, which is also collinear with the S4. Am I making sense? Hmm? So you should be able to do these things. Like, for example, instead of methane, if I give you alene, alene has suppose if I ask you, does it have an s-axis, a proper rotation axis? It may not be obvious when you write it in the way I'm writing it. So you need to,
Yes.
again, look into a different picture here. See that hydrogen and this hydrogen and another hydrogen. So those are the 4 hydrogens, right? Now, if you look at this axis here, that's the midpoint of this plane, this carbon atom, and the midpoint of the bottom plane here. That's your C2 axis for the molecule, right? That C2 is also collinear with an S4. Very similar arguments to that of the methane we talked about. Although structurally they are different molecules, from a symmetry consideration, they seem to share some symmetry elements. Does it have a reflection plane? So you have to start practicing, folks. I'm a little worried about some of you who are not answering these questions.
Would be along the carbon bonds, the reflection plane.
You mean this plane is a reflection plane, for example? Is that a reflection plane?
I thought it would be along the carbon double bonds, horizontal.
It's quite interesting. That's not where it is. In fact, if you draw a line between these atoms, right, these hydrogen atoms, the diagonal of the plane, and then come back and write another diagonal right here, the bottom plane, that is a reflection plane because that reflects 2 of these atoms. And similarly, there is another one. If you want to write using these 2 things, similar looking one, you have another reflection plane. So you have 2 reflection planes here.
Would the second reflection plane be the bottom 2 hydrogens, like
Correctly.
encompassing those?
Yes.
Okay.
Yes. In other words, the reflection plane contains 2 hydrogen atoms. And the next one contains these 2 hydrogen atoms. Okay, I'm going quite a big on the improper axis of rotation because that is something that people may have some issues. Other things are easily visible because here we are doing 2 operations together to get the molecule into its original form.
So Professor Chari, so for an improper axis, it has to have 2. So it has to have some type of axis rotation and then a reflection.
Yes, S4 means it should have a C4 and a sigma.
So like with the methane, it was the plane was like right in the middle of the cube.
Right.
Is that how you drew it? Okay.
This one is not exactly a cube, right? This is more like a cube that is elongated along one direction. So these ones are called tetragons, not exactly a cube. They're equal on two sides. This side and this side is equal, but that side is not equal. So this is a geometry in which x and y are same, but z is different. In cube, all x, y, and z are equal. So different geometries. Let's take one more example before we move on to the next topic. Ethane in staggered configuration. Okay, you all know that ethane can exist in two forms, right? Eclipsed and staggered. Eclipse means the hydrogens of that bonded to both carbon atoms lie in the same line, and a staggered one, they are offline. So one way to represent that configuration is and SC2. So there is a triangle in which we have a line forwarding, and here is a triangle that the one of the corners of the triangle is facing us. So there is a point, only one hydrogen is facing, here two hydrogens. So that is a staggered form of ethane. If it is eclipsed, both the triangles are exactly identical. So does it have an S? I know it has a C3. The carbon-carbon bond, that direction of the CC bond is a C3 axis of rotation. But my question is, does it have any S? Am I making sense here at all, folks? There's another example. These molecules stereographically may look very different, but they share some symmetry elements in common. That's what I'm trying to drive at. I would claim that the CC bond axis here, this line, CC line here, I claim this to be S6. What does S6 mean? You have to have a C6, right? Followed by a sigma. Can you all see this? So the way to appreciate anything is just to draw the structures and see if that makes sense. So if I were to do a C6 here, what would that do to the molecule? So this is 120 degrees, right? But I'm not rotating by 120. How many degrees I'm rotating this molecule by when I say C6?
60.
60 degrees. When I do this 60, what happens is this hydrogen comes forward, right? So, and that those two hydrogens go back. So that looks something like this. And similarly, these two things come here and that hydrogen goes back. And then C and C. So you have hydrogens here. If those of you want to have more accounting, you can call this hydrogen 1, 2, 3, and then we can call this 4, 5, and 6. There are 6 hydrogens in this. So when you rotate by C60, the H1 comes here, H2 goes there, H3 goes up there. And H4 comes here, H5 is here, H6 goes back. But this does not look exactly similar to this, right? However, these two structures are related by a simple reflection plane. Suppose if we were to reflect this molecule along a plane that is perpendicular to the CC axis, when I do that, this goes down and that goes up. So the resulting structure now looks like, and then this comes down here. And to maintain the labeling, what will happen is the H5, the H4, and the H6 go up, and the H1 and H2 and H3 come down. Yes, when you put the labels on the hydrogens, they may not look exactly the same. But if you remove the labels, both are indistinguishable. Because all hydrogens are equal, the only reason you're able to say any difference is because you label them. But if you remove the labels, that is the situation in nature, right? Nature does not put the labels. It tries to say whether the molecules look similar or not. Now these two look similar. So that's an S4 or S6. Am I making sense here, folks? It does not have a C6, it does not have a sigma, but then when you do both, C6 followed by sigma, you see a similar looking configuration. So the resulting structure looks apparently unchanged from the original one. So we say that symmetry element is present. So this one has an S6 operation. I'm giving you different examples just to give you an idea about how to go about structures. The more the examples, more solid, now you will have understanding of this. Does it make sense to all of you folks? The examples we have taken so far?
Professor, I have a question.
Yes.
When I was looking at the notes, it said note that S1 equals sigma, S2 equals I for inversion, and then it says, and sometimes S2n equals Cn. If we have like a C6, it ends up being followed by a sigma, it ends up being S6. So do we not multiply n by 2 for the S2n?
Yes, S2n sigmas, yes. So you can also call this, what is S1? Basically, S1 is C1 followed by sigma, right? Correct? C1 is what? Doing nothing, correct? Rotating the molecule by 360. So S1 simply means sigma. S2, for example, is C2 followed by sigma. In some molecules, yes, this can be an I, but some molecules it doesn't have to be. But this is an independent operation of I. I is a very independent symmetry operation.
Okay.
But in some molecules, yes, it is. Basically, what happens is, if I do S4, that is C4 followed by sigma, right? So if I do S4 4 times, that is C4 4 times followed by sigma 4 times. Watch, this 4 is an even number, right? When it is an even number, C4 4 is E, doing nothing. And sigma, when you do reflection even number of times, you get again identity operation. So S4 4 is an identity operation. Let's do S3. S3 is C3 divided C3 followed by sigma, right? If I were to do 3 times, what happens is S33, C33 is identity, doing nothing, but sigma 3, when you do odd number of reflections, right? You still have a sigma here. So S33 is a sigma, S44 is E. So when it is an even number, then S44 is an identity. When it is an odd number, and if you do 3 rotations on S3, the resulting thing is a sigma here. That's what we were talking about in the lecture there. Does that make sense?
Yeah, that does. Thank you.
That means when we say 2n, 2n means it's an even number, right? When it is an even number, 2n, then S2n 2n becomes identity. If n is an odd number, S2n 2n, SNN becomes a sigma. Are we okay with this so far, folks? Any other questions? If not, I'll give you some molecules and ask you to predict the point groups, okay? Let me give you sulfonyl fluorochloride, SOFCl. What should be the point group of this? We went through this chart, right? In the lectures, I think you must have uploaded. So this is a practice now. What's the first thing you need to do, folks?
Draw the Lewis structure.
Draw the Lewis structure. And what's the next step you need to do?
Know what the central atom is?
Know what the central atom is. What's the third step? You need to have the Vesper model, right? Geometry, correct? The molecular geometry. And once you have the molecular geometry, then you have to do the symmetry operations. Once you have the symmetry operations, you know which ones are present, which ones are absent. And you have to go through the decision tree that we talked about in the last lecture. So that decision tree will help you to decide which point group this molecule belongs to. So it's a lot of work that goes on in each molecule. But this is fun. Can anyone help me with the Lewis structure of this molecule? Which one should be the central atom here? Which of these atoms is least electronegative?
Should it be sulfur?
You're absolutely correct. And how many bonds fluorine and chlorine like to make in the molecules? In general, fluorine and chlorine make how many bonds? 1 or 2?
I don't think they make a bond. No bonds.
I mean, this molecule has to have bonds, right?
Yeah, but not between fluorine and chlorine.
Fluorine and chlorine, because there's only one chlorine in the molecule, so there are no fluorine. All should be bonded to the central atom, correct? So the oxygen, fluorine, and chlorine should be the terminal atoms in the structure. That's how you write the skeleton. Right? So the way it happens is sulfur is the least electronegative. And then you have to have oxygen, and you have to have a fluorine, and you have to have a chlorine. But that's a skeleton. That's not the completed Lewis structure. So what does a complete Lewis structure looks like, folks? Although I'm giving only one example, this is the same protocol that you follow for any molecule. Although there are a million molecules that you may know, all of them have to be vetted through this process. Write the skeleton, write the complete Lewis structure, find the VSEPR, find the molecular geometry, and then keep going through the decision charts to see what symmetry elements this molecule has. And finally, based on the presence or absence of the symmetry elements, you assign a point group. So if your Lewis structure is not correct, then your analysis is going to be wrong. So what's the final Lewis structure of this molecule?
The oxygen is going to have a double bond, and the sulfur is also going to have a lone pair.
And how about the fluorine and chlorine? They will have octets, right?
Yes.
Do you all agree with him?
Yeah.
The oxygen exists as a single bond sometimes, correct?
Sometimes, yes. But oxygen likes to be double bonded because oxygen loves to make two bonds. Remember, oxygen is in the group 6. Generally, elements in the group 6, 6 minus 8 is 2, right? So they might like to make two bonds. If you have nitrogen, group 5, they like to make 3 bonds. If you have fluorine, chlorine, bromine, they are in group 7, so they like to make 1 bond. There are occasions where oxygen makes single bond. In that case, the oxygen will have a formal charge. But then we also know by rules that structures that have least distribution of formal charges is the most stable structure. So in this one, it has to be S double bond O. The extra 2 electrons on the sulfur makes a big difference. So what should be the electronic geometry around sulfur?
It's going to be tetrahedral and trigonal pyramidal.
The electronic geometry is tetrahedral because there are 3 atoms in 1 lone pair. 3 plus 1 is 4. That's what the steric number of this central atom is. If the steric number of the central atom is 4, then it has to be sp3 hybridization. And then because it has a 1 lone pair, so the resulting geometry will be trigonal pyramidal, very similar to ammonia, right, guys? Ammonia has the same arrangement. And if you don't do your math correctly, if you don't put that lone pair on the sulfur, suddenly it becomes a planar molecule. That lone pair does not make this molecule planar, but instead it makes it trigonal pyramidal. So we will have now a structure with sulfur, that's the trigonal pyramidal geometry, just like ammonia. It's like a tetrahedra without the stem, right? If you were to imagine a tetrahedra is like a camera tripod, this trigonal pyramid structure is a camera tripod without the stem. So the resulting structure looks like a pyramid, right? With a triangular base. It's a 3-dimensional geometry. Only oxygen, chlorine, and fluorine stay in the plane. Sulfur stays above the plane of the triangle formed between O, F, and Cl molecules. So does it have any rotational axis of symmetry? Does it have any reflection planes? Does this molecule belong to any special groups like tetrahedra, octahedra, icosahedra, linear, any of those? Right? So the next question that we want to ask is, does it have a rotational axis of symmetry? Does it? Ammonia had a C3, but this one will not, because in ammonia, all 3 atoms are equal. But in this, they're all different, so it does not have. The next question that you want to ask is, does it have a sigma? Does it have a reflection plane? Ammonia had 3 reflection planes, right? Each reflection plane containing 1 NH bond. But do we have that here? No. No reflection planes. Does it have an inversion center? Is there a point of inversion in this molecule? No. So what should be the point group for this then? You have the chart in front of you, right? Learning should not be always me talking, doing, and giving you the answers. It has to be mutual. This is not a game. This is not a spectator game. This is a game where the teacher and the students are players. We'll play the game together.
This is C1.
You are absolutely correct, sir. C1 has absolutely no symmetry whatsoever. So this molecule belongs to C1 point group. All right. Is that clear to all of you? So this is the most asymmetric molecule you can think of. Absolutely no symmetry at all in this. Let's look at another one. Boron, FCl, Br. Fluorochlorobromoborane. What is unique about boron containing compounds, folks? By now you should know. Three possibilities, right? Octet expansion, octet deficiency, or octet precise. To which of these categories boron belongs to? Go back to the examples of boron that we have done.
Follows the octet rule.
Hmm?
Follows the octet rule.
They follow or they violate?
Should follow.
You mean boron will have 8 electrons around it? Is that how your boron look like, BH3 or BF3? We have done BF3s, right, in the past? Can you go back and check those Lewis diagrams?
Isn't boron deficient? So it's less than the octet?
Correct. So what do we call this? Octet deficient molecules, right? That is true with not only the boron, but all the elements in the boron group. The boron, the aluminum, the gallium, and all that, right? Hmm? So what should be the Lewis structure of this interesting molecule?
Wouldn't it have 3 bonds on the boron?
Hmm?
Wouldn't the boron have 3 bonds attached to it?
Mm-hmm.
And 2 lone pair.
And lone pair where? On boron?
I think so, yeah.
How do we know whether it has a lone pair or not, folks? What is the rule that we follow? How many total number of valence electrons this molecule has?
3.
No? Total number of valence electrons.
3.
Boron has 3, fluorine is 7, chlorine is 7, bromine is 7, right? What's the total here?
24 total.
Hmm? 24, is that correct? So when you draw the Lewis structure, that structure should not contain more than 24 electrons because electrons cannot be created nor destroyed. You can only redistribute. You can't simply put some extra electrons because there is an octet deficiency. That's not how we do. Your final Lewis structure cannot have more electrons than the total number of valence electrons this molecule has. Law of conservation of mass. Right? So when you put the structure here, boron, fluorine, chlorine, bromine, when you put the octets around them, each atom has 6 electrons and 2 electrons in the bond, right? So each fragment in this molecule carries 8 electrons. So 8 plus 8 plus 8 is 24. That is the reason why boron cannot have a pair of electrons. So this is why we call this an octet deficient molecule. Would you all agree with me? Are you
Yes.
all okay with this? This is how we know, whether to put a lone pair on the boron or not. You can't put electrons just like that very carelessly. We just have to be very careful, mindful of how many total number of valence electrons I have, and that's all I have to distribute to make the bonds. Okay, so what kind of a geometry is this? 3 atoms and no lone pairs. Steric number 3. So the geometry should be
Trigonoplanar.
trigonoplanar. Thank you very much. See the difference between SO, FCl, and this molecule. The previous example, we had a molecule that was trigonal pyramidal. Now this is a molecule that is trigonal planar. All right. So that's the geometry 120 degrees. Does it belong to a special group like tetrahedra, octahedra, linear molecules, or icosahedrals? No, right? So the first question that you ask yourself is, does it have a C, a rotational axis symmetry?
No.
Can you rotate this molecule by any degree other than 360 to achieve a configuration that looks similar to what we started with? It's a long, winding question, but that's the most accurate way of asking it.
I would say no.
There's none, right? Very clear that this molecule has only C1. All right. My next question is, does it have a reflection plane?
Sigma V.
Hmm?
It has a sigma V.
We can call that sigma V or sigma H, but definitely it has a reflection plane. What's the plane? The reflection plane is the plane of the molecule itself, right? All planar molecules of necessity will have at least one reflection plane, that plane being the plane of the molecule. So it has a sigma. So what should be the point group of this molecule?
CS.
You are absolutely correct. Am I making sense here, folks? Yeah? Let's look at another molecule. You all know this molecule, right? What's it called? Carbonate. How many total number of valence electrons this has? 1 carbon, 3 oxygens, and 2 negative charges. Because I see some of you writing.
24.
Hmm?
24.
So carbon has 4 valence electrons, 3 oxygens. Because there's a negative charge of 2, you need to add 2 electrons. So that will be 18 plus 2, 20 plus 4, 24. 24 electrons. Just exactly the way we had for the BFClBr, correct? BFClBr also had 24 electrons. So is carbonate anion. All right, so what's the next step? You need to draw the most possible Lewis structure. How does it look like? Yes.
So would the carbon be in the center and then attached to the 3 oxygens? However, only one of the oxygens would have a double bond, the rest would be single. Would it be like a resonance structure, sort of?
Absolutely correct. So this has 3 atoms and 4 bonds, right? So the bond order is going to be 1.3. Okay, so does carbon have any lone pair of electrons on top of it?
No.
So this one will have the first approximation. This is how it should look like. If I write the formal charges, which is the number of valence electrons minus number of non-bonded electrons minus 1/2 of the bonded electrons, this will have -1, that will have -1. That's why the charge of carbonate is total of -2. But then because of resonance, the way we write this structure is basically like this. This is a 3-atom 4-bond situation. So the bond order is number of bonds divided by number of atoms. We have 4 bonds and 3 atoms. So the average bond order of this molecule is 4 divided by 3, which is 1.33. So there is not a single bond or a double bond. All bonds are equal. There are slightly more than 1 bond, a single bond, less than double bond. So average bond order is 1.33. So this is the state. So what should be the molecular and electronic geometries of this? Three atoms. No,
Trigonoplanar.
that should be trigonoplanar, just like the previous molecule BFClBr, right? This is also trigonoplanar. The only difference between BFClBr and carbonate is, in the carbonate, this is an octet precise molecule. It's not efficiency. All right, so does it belong to any special groups like tetrahedra, octahedra, linear, or icosahedral groups?
No.
No. So the next question is, does it have a C? Does it have a C or no?
Yes.
What's the highest fold rotational axis of symmetry this molecule has?
C3.
C3. Correct. My next question is, do we have 3 C2s perpendicular to the C3?
Yes.
Where are the C2s?
Along the CO bond.
Along the CO bond. Each CO bond acts like a C2 rotational axis. Because I have 3 CO bonds, so I have 3 C2s perpendicular to. My next question is, does it have a sigma h? What is sigma h again, folks? Remember the three sigmas, I gave you the definition, sigma h, sigma v, and sigma d. For a molecule to have sigma h, what's a plane of reflection perpendicular to the highest fold rotational axis of symmetry. The highest fold rotational axis of symmetry, here it is C3. The C3 is perpendicular to the plane of the molecule, right? Because this molecule is planar, the plane of the molecule itself serves as a sigma h. So the answer is yes, it does. So if it has Cn, n number of C2s, and sigma h, this should be DNH group. So this one then should be D3H. So carbonate belongs to D3H.
Professor, I have a question.
Sure.
You said the sigma h, and before you said sigma h and v can be argued. Like, how would you know if it's sigma h or v? Forget.
Okay, here is the, can somebody answer that question? I'm doing too much of talking here. How do we know, how do we distinguish between sigma h, sigma v, and sigma d?
I understand the difference, but I'm kind of struggling on how to explain it because I feel like it's more of a visual thing.
No, we can also formalize, articulate it, right? Scientific articulation. Yes, we can articulate. Please try, and I'll try to help you.
So for sigma D, if it has more than one C2 and the C2 is not equal to the principal axis, it must and has diagonal slices,
Mhm.
then it would be sigma D.
Can I make it much simpler than this?
Yeah.
If here is the condition for sigma D. A sigma D contains the highest fold rotational axis of symmetry, and it is a plane that bisects the bonds between atoms. So two conditions for sigma D. It must contain the highest fold rotational axis of symmetry the molecule has, and that plane must be bisecting the bonds between atoms.
Actually, Professor, I have a quick question.
Yes, Fatima.
The Alene example we went over, we said the reflection planes were sigma. Were you saying those were sigma D examples?
That's for sigma D's, yes. We'll get back to that Bilene example. Maybe the next one we'll take Alene as an example, but first let's finish this. Okay, now sigma V. What's the difference between sigma V and sigma D? Let's look at what is common between them. They both contain the highest fold rotational axis of symmetry, right? Except sigma V's do not bisect the bonds.
I have a real quick question.
Yes, sir.
So you said for the sigma T, it has to contain the highest form of rotational axis of symmetry. When you say that, you mean like it has to be perpendicular to it, or it has to run along?
It has to be parallel to the plane.
It has to be parallel to it?
Yeah, or it should be containing that axis.
Containing it like...
Okay, let me show you an example.
Yeah. Thank you.
Let's say if this is a plane, right? If the axis is contained in the plane, then we say it's parallel. On the other hand, if I have a plane axis perpendicular to the plane, look at the way I'm holding my marker here, right? The marker is perpendicular to the plane.
Right.
Then that is not containing the axis. It is normal
Okay.
to the axis.
Okay, it's normal. Okay. Thank you.
Make sense? Okay, good. All right. So that's the sigma v. So what is sigma h then? If you have a plane perpendicular to the highest fold rotational axis of symmetry, if a molecule, in this case is C3, the C3 is here, perpendicular to the board, right? And the plane of the molecule is in the plane itself, the board itself. So that is a reflection plane. For that reason, we say there is sigma h. Gurveer, does it make sense? You may
Yes, a
have
little more.
one more thing you have to keep in mind. You may have multiple sigma v's and multiple sigma d's, but in a molecule, you cannot have more than one sigma h. Because by definition, when you're looking at a plane perpendicular to the highest fold rotational axis of symmetry, there must be only one plane. You may have 2 sigma v's, 3 sigma v's, but you will not have 3 sigma h's or 2 sigma h's. There is only one. That is a unique plane. Gurveer, does it make sense?
Yes, a lot more. Thank you.
Yeah. For example, if I'll, is this clear to all of you? It's a D3H molecule, okay? Suppose if I have benzene. If I ask you, this is a molecule that has sigma V's, sigma D's, and sigma H. Can you identify how many each we have? What's the highest fold rotational axis symmetry this molecule has?
C6.
C6. And where is that C6? Is it in the plane of the board or is it perpendicular to the board?
It's perpendicular to the board.
Perpendicular to the board. That's beautiful. That's a C6. Does it have C2s?
Yes.
Where are the C2s?
There would be 6, right?
Yeah. Where are they? Are they perpendicular to the board or are they contained in the board?
They're in the board. They're
in the board, right? Okay.
yeah.
So there are 6 C2s. And how many sigma V's it has? And does it have a sigma H?
Yes.
And what is the sigma H here in this case?
It's along the plane of the board.
Yeah, it's the plane of the board itself. The molecule itself, because it's a planar molecule, we have a sigma H, one sigma H. Does it have sigma V's? If you can think of a plane that joins these 2 carbon atoms and comes around this, that's perpendicular to the board here, which means it contains the C6. Because C6 is here, right? And now we're talking about a plane that contains the C6. So that plane comes out like this, perpendicular to the board. That is a reflection plane. So you have 3 sigma V's. These two, and those 2. In addition, you also have sigmas that bisect the bonds between carbon atoms. Let's say these two carbon atoms in the midpoint. That is bisecting the bonds here. This is also a plane that contains C6. So this plane should be called sigma D. Fatima, would that answer? Oh, is that clear here? How do we distinguish between a sigma V and a sigma D, right? It has 3 sigma V's, 3 sigma D's. So overall, this molecule will have a symmetry of D6H because it has sigma H, 6C2, C6.
So just to clarify, the sigma V does not bisect bonds, right?
Correct.
Okay.
In fact, if you look at the sigma V, it contains more atoms than sigma D, right? Because sigma D does not contain any atoms here. Because it's bisecting a bond, so you have the atoms on both sides of the plane, but not on the plane. In sigma V, they stay on the plane. Another way of looking at it. Are we clear here, folks? It's an interesting thing because we're going to use this in the next course, those of you who are taking advanced inorganic chemistry, to look at these symmetry elements and work out a very beautiful way of knowing the state of hybridization. So that is called symmetry adapted linear combination of atomic orbitals. There's an elegant way of showing it. We're not going to work on that in this course because we have other topics to cover, but there are going to be applications of this too when you go into the advanced courses. That's the reason why it's important to get it right now. And I gave you so many examples, right? Lots and lots of examples. Am I making sense here, folks? So this is how we should be able to look at the molecules and like chloroethene. For example, if I have Cl, C double bond CH, what should be the point group of this? This is an example. I have more than one central atom in this, or 2 of them.
Can you repeat the question?
What's the point group of this molecule? Before that, we need to know what's the molecular geometry of this, or the shape of this molecule. By looking at it, what should be the shape?
Linear.
Linear. It has to be, right? If you look at this carbon is connected to 2 atoms, no lone pair, steric number being 2, it should be linear. So that angle should be 180. The same applies to this carbon too. So they're all linear. So this angle here, ClCc and CCH, that bond angle, both are 180 degrees. So that's a linear molecule. It belongs to a special group. And a hydrogen here, so you don't have C2s. So we don't have C2s. And you have, of course, infinite number of reflection planes. You have that plane, infinite number of planes that contain all these atoms. So they have infinite number of sigma V's. There's no sigma H on this molecule. If there were to be a sigma H, then that plane that is perpendicular to the C infinity axis should be a reflection plane, but it is not, because I have chlorine on this side and I have hydrogen on that side. So suddenly I find this molecule has C infinity, infinite number of sigma V's, but there is no sigma H, so the point group of this will be C infinity V. On the other hand, if I were to replace one of these hydrogens with chlorine, then the story is different. Then you have both C infinity and infinite number of C2s, which are perpendicular to the C triple bond C, normal to the direction of the board, orthogonal to the direction of the board. It's 90 degrees vertical to the CC bond here. Different ways of saying it. So that makes it, suddenly if that is yes, and then that plane becomes your sigma H, perpendicular to C infinity V, suddenly that point group changes to what we call D infinity H. Just one atom changed, right? Suddenly the point group changes. The monochloroethylene is polar molecule, but dichloroethylene is nonpolar, because molecules that belong to the D groups cannot be polar.
Professor Chari,
Yes.
so when you look at the picture for the tree of all the things, the yes or no, so it's yes and then the D sigma H. Is that because there's a center of inversion now with the two chlorine?
No, it's not a center of inversion. Remember, for the D infinity groups, we need to have C infinity and infinite number of C2s perpendicular to it, right?
Okay.
Because if you look at this, that is your C infinity, right? Right?
Yeah.
So you have, if you look at now axis in the plane of this molecule, that's a C2, right? And in fact, there are several C2s, all of them do 180 degrees rotation. They give you the same looking molecule. So D infinity H may sometimes, it may contain the inversion or may not, but the most important thing is having a sigma H and Cn and a number of C2s.
Wait, can you repeat that again for D sigma H?
D sigma, it should be C infinity, infinite number of C2s, and a sigma H.
Okay. Thank you.
Is this helping you folks to understand a little bit better than before?
Yes, sir. It's helping a lot.
Hmm?
It's
Yeah.
helping a lot.
Because I'm not taking the same example, I'm giving you different examples and then using the same principles over and over. I'm not teaching you new stuff here today. We are using the principles that we have learned in the previous classes and apply them to different molecules and be able to accurately assign the point groups. Suppose if I ask you, what is the point group of furan or thiophene? Sometimes it's also known as THF, tetrahydrofuran, because there are 4 hydrogens on this. It's not a linear molecule, it's not octahedra, it's not a tetrahedra. It's not icosahedral, so does it have a C? Serena, do you see a C here? I don't see you, but can you see a C here? I'm not sure if they are in the class or not. Jared, I don't see you, but do you see a C in this furan molecule? Jared Stefan. I'm sorry, I don't know. I don't think some of these people are.
They're
Yeah,
saying
they're texting in the chat.
They're putting in a chat. They can talk. You know, your audio is visible, folks. You can use the audio because my screen here is too small to see the attendance list and the videos of the people.
they both said yes.
Yes. Okay, where is that C2, folks? We're running out of time here, so let's do it very quickly. If you look at that molecule, that line that contains the middle of the CC bond here and the oxygen atom in the plane of the molecule is your C2, right? You don't have a plane perpendicular to the C2, so it does not have a sigma H, but it has two sigma V's. One sigma V is this. Because the molecule is planar, it has the plane of the molecule itself as a sigma V. So it has a C2 and two sigma V's. That makes it very similar to water. So the point group here should be C2V. You see how many examples were taken? CS to C1 to CI to D3H to C2Vs, C3Vs, C1s, CIs. Okay. You don't have to memorize all this stuff because you will be allowed to use this flow chart, but you need to write the correct geometry and be able to apply the principles and answer the question. Is that okay, folks? Next week, next Monday onwards, we will be, I'll be uploading something on the coordination complexes, just some general lecture on that. And then we will continue with the different aspects of the coordination complexes next week. That will take about 2 weeks. So coordination complexes, molecular orbital theory, and the point group classifications will be the content that will be tested on the exam number 2. Is that okay, folks? Is that clear? So all that we have been doing in this class and the previous couple of classes will be a part of the exam 2. So with that, I thank you all for joining the class, and keep doing, folks. It may be difficult in the beginning, but once you start getting things right, you will enjoy this. This is a great topic. It's very important in chemistry. It gives a very different perspective of molecules than what you have been learning before. And the beauty comes in when you try to tie things together, the symmetry of the molecule and several functionalities, like NMR, IR, Raman spectroscopy, how people interpret the spectral features of molecules based on the symmetry point group classifications. It's an amazing science. All right, so we will see you all next week and enjoy the rest of the time. Bye now.
Thank you.
Thank you, Professor. Have a good day.
Thank you very much. Thank you very much.
Thank you, Professor.
Thank you.